So yeah, it should be start recording. Okay. So hello everyone, welcome to our week 3 SPAAM seminar series. So our first speaker today will be Hanson Bharth, who is a PhD in MASDOC, and he will be talking about mathematically modeling metal sheet spinning today. So I'll let Hanson to take over. Hanson, please.
Okay. Yeah, so I'm Hanson, talking about mathematically modeling metal sheet forming. And this is joint work together with Dr. Ed Bramwell. Okay, so does this work? Okay, so an outline of what I'll talk about today. First, I'll give an introduction, then I'll go into the model formulation, and then I'll talk about the techniques that we use to solve it. Then we'll look at the example of full slip as a simplifying case, and then the results and a conclusion. So why should we care? So currently to tackle climate change, there are mainly two ways. The first of which receives nearly all the attention of research, is to use energy sources which use less CO2 emissions. And the second way, which motivates our research, is to come up with new processes which use less energy. So why metal? So global leading sources of CO2 emissions from energy processes sees the industrial sector as the largest contributor. If you refine that further, then the metal industry is the largest contributor. So tackling the CO2 emissions from metal industry is a good way to start. And just to give you an idea of the scale of that, world production of steel is 1.4 billion tons, and that's per year. So you can average that for global population, and that's about 200 kilos of steel, which is produced per person per year. This is globally, so that's a bit ridiculous. So one thing we should be thinking about is how can we be more efficient with the material that we're currently producing. An example that I'll go into is car doors. So with steel car doors, 50% of the material that's used is wasted, whereas with aluminium car doors, 60% is wasted. And it's in fact theorized that we can reduce the wastage by 30% without changing the end product. And we can think of this quite easily when we think that to make a car door, first the part has to be manufactured, produced from natural resources. And then bits are chiseled away and chiseled away and chiseled away from different manufacturers until you get the final product. So it would be better if we can go just to one place and make something much closer to what we actually want in the first place. So this is where metal sheet spinning comes in. So here, can you see the video? So here we have a video of metal sheet spinning. This is flexible metal sheet spinning. So this is a new process that's been designed. We have a metal sheet clamped between these two arms, and then these two rollers are applying pressure to this metal sheet incrementally to deform it into a certain shape. So we see actually that there's only a small amount of deformation every revolution of the metal sheet. So in that sense, we see only a small amount of permanent deformation. And this is actually different from the traditional process. So this is a new process, differing from the traditional process, whereas the traditional process has a predetermined shape, does away with two rollers, and just rolls to the predetermined shape with one roller. What that means is that traditionally we can't design shapes ad hoc. So this is the big advantage that we have from this new flexible metal sheet spinning. So we have the machine, what's the problem? Okay. So here we have a simulation of metal sheet spinning. I think this is done in finite elements, and this has been taken in the order of days. So what we end up seeing here is some wrinkling starts to occur. So this wrinkling is instability that's formed, and it's not really clear why that's happened. So actually in mass production, we can't really use this process because these instabilities form, and because this simulation takes the order of days to run, you can't do that in a real-time control loop. So actually what we need to do now is do some more work in the physics and the maths to understand where these instabilities form and prevent them. Okay, so I'll go into the model formulation. The actual metal sheet spinning subject to the rollers is actually really difficult to model. So we're going to look at a simplifying case, one which is an elastic half space being deformed by a rigid cylindrical roller. And that looks something like this. So here we have a cylindrical roller and the metal media or elastic half space going over the top. So we take a frame of reference fixed with the cylinder, so it seems as though the metal media is translating over the top. So our model setup. So we have a coordinate system X and Y with a frame of reference fixed with the center of the cylinder. Displacement U in the elastic media with stress tensor tau in the elastic media. Rolling cylinder with radius R, rolling at angular velocity omega hat, and a velocity of the elastic media Q. Okay. And how do we actually model the contact with the cylinder and the elastic half space? Well, actually, friction is something which isn't entirely well understood and is an active area of research in itself. But for our purpose, we'll be looking at stick-slip model of friction, which leads to a fairly complicated mixed boundary value problem. So for our boundary conditions, first we assume that outside of the region of contact with the cylinder and the elastic half space, it's free from stress, or there is no pressure acting on it. So we have a stress-free region here. Then in our next region, we have that the cylinder is slipping beneath the elastic half space, in which it experiences a frictional force from the slip. So here we relate tangential and normal forces via a coefficient of friction mu naught. And here, because the slipping is backwards, with the slipping being in opposing directions, we're taking a negative coefficient of friction. In the next region, we have a stick region. So the elastic half space in the cylinder has the same velocity, which is in a really complicated way. And then the next boundary condition, we have another slip region, again relating the tangential and normal forces via a coefficient of friction, but this time it's positive because we're slipping in the same direction. And then finally, throughout the entire contact region, we have a contact boundary condition, essentially saying that the elastic half space cannot go through the cylinder. Okay, so that was a really complicated boundary conditions. Even if we linearize it, it's still fairly complicated. The boundary conditions themselves are probably not too much to remember. I guess the main takeaway is we end up with a complicated mixed boundary value problem where there are two boundary conditions in each region. And I guess another point is that these points minus A, minus B, C, and D are unknown and to be solved as part of the solution. Say, for example, if you push your thumb into a sponge, you don't know where the material of the sponge stops touching your thumb, right? And so to find out where it stops touching is part of the solution. Okay, so what's our governing equation? We're assuming linear elasticity in the elastic half space, where rho is a material density, lambda is Lamé's parameter, and mu is the shear modulus. And we gathered this momentum term from the translation of the elastic media over the top, resulting in this governing equation. I guess the main takeaway here is this is a linear PDE, and we can solve this from using Fourier transforms. So to summarize, we have a linear PDE, which we can solve from doing a Fourier transform, and a complicated mixed boundary value problem. Okay, so what's our solution procedure? Our plan is to frame this problem as a Wiener-Hopf problem. I'll go into a bit of detail on how we actually do Wiener-Hopf. Okay, so we can find a general solution by taking Fourier transforms of the governing equation. This results in this solution, where a hat and b hat are the unknowns, which we can find from Fourier transforming the boundary conditions, and the rest of the guys are known and here, but they all look horrible, so you probably don't want to look at them too much. Okay, so for tackling the Wiener-Hopf, we first need to come up with some definitions. So we define half-range transforms. So we can define a half-range transform in relation to a full-range transform centered around the point L, by taking a full-range transform at the point L, and separating this into the integral from infinity to L, and then from L to minus infinity. From infinity to L, this results in a function which is analytic in the upper half plane, and from L to minus infinity, this is a function which is analytic in the lower half plane. Okay, so how does this help us? Well, once we define an unknown function phi plus, analytic in the upper half plane, so we define this such that its region of analyticity includes the real axis. Then we can also have our defined function analytic in the lower half plane, phi minus, also including the real axis. And because there's an overlapping region of analyticity, we can form an equation with phi plus and phi minus, which is defined in this overlapping region of analyticity, where A and F is entire. And our stages from here is to multiplicatively decompose A into its upper and lower components, and then additively, and then divide through by A plus, then additively decompose the resulting. So we multiplicatively decompose A, divide through by A plus, and then we additively decompose F over A plus into its upper and lower components. Then we can rearrange this, so we get all our plus functions on one side and minus functions on the other side. And then from analytic continuation, we can get that there's a function jk which is equal to this. And then because typically we have decay of either our plus functions or our minus functions, and we only need one of them to decay in their respective half planes at infinity, then we can apply Liouville's theorem and set jk to 0. This allows us to solve phi plus and phi minus. And I guess a nice thing that we get from here is we can solve a problem with two unknowns with one equation. Okay, so this is the method that we use. So the original limit of stick-slip friction is fairly complicated. So we look at a simplifying limit of full slip. So instead of having stick-slip regions for friction, we just have slip throughout the entire contact region. This gives us something a bit like this, where actually we can rewrite some of our stress-free boundary conditions such that you have slip throughout the entire surface. What this does is it reduces the number of jumps in your boundary conditions, and the number of jumps within the boundary conditions leads to the size of your matrix Wiener-Hopf. So we've gone from having 4 jumps in our boundary conditions to 2 jumps in our boundary conditions, which leads to a 2x2 matrix Wiener-Hopf. So we can transform all this, resulting in the following matrix Wiener-Hopf, where we essentially have something similar to what we had before, but we have a vector of phi plus, a vector of phi minus, a vector of the forcing term, and matrices as our factors that we need to multiplicatively decompose. But the trouble that we have here is with matrix factorization, it's non-commutative, so you can't apply the same approaches that you do in scalar Wiener-Hopf. And actually, you can only get an exact solution in matrix Wiener-Hopf in very few cases. And unfortunately, this isn't one of those cases. So we have to use approximative techniques. Again, so the frictional case would have led to a 4x4 matrix Wiener-Hopf, which I think until the last year or two, the largest matrix Wiener-Hopf which has been solved is 3x3. So the 4x4 one is really hard to solve, basically. So our approximative technique that we use here, so in our strip of anorticity, we can choose an inversion contour near the top or bottom of the strip. If we choose a contour near the top or bottom of the strip, then either one of the exponential terms would be very small. So we can approximate the exponential term to be 0, and then treat the scalar equations within the matrices as scalar Wiener-Hopfs and solve initially that way, and then add in the exponentials and iterate until convergence. But I won't really go into too much detail. So how do we actually compute some of the decompositions? Well, we compute decompositions via the Cauchy transform. So say we have a function f. We want to split f into f plus and f minus. So we can take a Cauchy transform of f plus, where the contour gamma plus is below k. And then for f minus, we take the contour gamma minus above k. And this results in our Cauchy transform. But we actually have to do quite a lot of these decompositions, and it's quite impractical to do so analytically. So we want to find a way that we can do this computationally and accurately. To do so, we can actually use orthogonal polynomial, a weighted orthogonal polynomial basis. So say we want to decompose, we want to take a Cauchy transform of a function f. We can expand f in a weighted orthogonal polynomial basis as such, and then we can take a Cauchy transform of f, which is essentially the same as taking the Cauchy transform of the weight and the polynomials. So we can actually, so one of the benefits of doing this is that the Cauchy transformed weights and polynomials satisfies the same 3-term recurrent sequence as the original weighted orthogonal polynomial basis. So this makes it quick to compute. And we typically do this computation. We take the Cauchy transform on the interval -1, 1, and map that to whatever contour we want to take. But again, I won't really go into too much detail on that. So we can do some nice things with some orthogonal polynomial bases. So what are our results? So here's a contour plot for some parameter values. So this is a plot of the displacement. What we end up seeing is far from the surface, there is pretty much no displacement, which you would expect, because the displacement would decay as you go further away from the source. And we get this wrinkling on the surface, it seems. And we can also, for the same parameter values, plot the profile of the pressure on the surface, which fits as we expect, that it goes to 0 outside of the contact region. And in fact, just to illustrate what we do for the free boundary problem, so we first take an initial guess of what minus A and D are. In this case, we guess that minus A and D are -20 and 20. And it sort of looks like it's a good guess, but actually we don't smoothly go to 0 at -A. So maybe we should come up with a better guess. So we can come up with a better guess and iterate basically the whole Wiener-Hopf process again with this new guess. Oh, and we actually see that we get something better. So one of the problems that we're having is in the full slip case, this iterative method seems to work okay. But when we go to the frictional case with 4 free boundary points, it seems as though we need to do something else. So it doesn't seem to work as well. So just to conclude, we've seen a derivation of a model for a rolling cylinder, discussed the Wiener-Hopf technique, and then seen some results in the limit of full slip. And then further work we've got to do from here is to look at solving this free boundary problem asymptotically. And by that, what we're really looking at is saying, okay, so if we're going near to these free boundary points in our solution, what does this mean for our transformed variables? And from considering the solution in this way, or an approach in this way, we're trying to see if we can discover more about what these points minus A, minus B, C, and D should be. And then once that's done, we will solve the full model or the frictional case. And then finally, we'd like to add in some plasticity. I guess by considering it as an elastic half space, we're considering it as a material which, when applied a pressure, deforms, but when you remove that pressure, relaxes back to how it was. Whereas if we add in plasticity, which is nonlinear, then we can add in some permanent deformation, which is actually what we end up seeing, but more complicated to do. Okay, so that's pretty much everything I wanted to go through. Here's some references if people are interested. Thanks for everyone's time, and have you got any questions?
Thank you, Hans.
So before we went to the Q&A session, let's unmute ourselves and upload for Hanson's talk.
I've got a quick question on your model,